and then we'll keep trucking. All right, everybody online can hear me? We're going to assume that's a yes. Oh, and we're so close now with the virtual machine. So the virtual machine server is up, is reachable on the network now, but we are having an issue getting a Ubuntu thing installed since we made the change to expose it to the external network. So I think that'll be fixed today. That should be something stupid. It's probably an easy thing, but then anytime you're on the CUWCS network, you'll be able to have it. And what I'll do is I know on Slack there's some talk about certain things not installed or having problems being working. What I'm going to do is I'm going to build an Ubuntu virtual machine that has Visual Studio code already on it, make sure it has all the compilers, code actually works, whatever, and I'll set that up as a template. So then when I give the tutorial in class for setting up the virtual machine, you'll effectively release your own virtual machine. You'll clone the template, and that will be a full working machine with all the stuff kind of good to go. So I apologize for the delay on that. We've had to work with IT in order to get the right kind of network thing set up where the rest of campus is protected from anything crazy we do inside. And so I think we're in good shape now, and the performance of the network seems pretty good. So it's just that last little piece now where you go to install Ubuntu and it says, I can't find a hard drive. You're like the one thing you just assume would work. it just doesn't work. So it's probably one just little configure piece. All right, so let me remind us of the bug from last time. So ignore some of the extra code I put in here. That was just my debugging. In fact, let me comment out some stuff. And then we'll walk through this. It's actually a good bug, and the warning tells us everything we need to know. So this is pretty close to what we had in class last time. So I think I was allocating what, 7. So I'm creating this is a old style C based string. So I'm representing a string as a char pointer. So that points to the base address of a string. So how am I doing that? I'm calling the memory allocate function, and I'm asking for 7 bytes of memory because size of char is a byte. All right, because in C and C++, char is a byte because it's represented the extended ASCII character set, 0 to 255, 256 unique characters. So this will give us a 7 bucket character array, which is our representation of a string. Okay, now this is actually the problematic line right here. S is equal to hello. I'm putting the string hello in there, right? All right. So then we went and we printed it out, and that was fine. This gave us the memory address. This gave us the actual string. This gave us bucket 4 from the string. Everything was fine. This is an alternate way of saying bucket 4. So all this was just fine. I'm going to comment out those two just so we can see that. So this lulled us into a sense of a sense of confidence, I guess. Last time, this warning popped up, said, oh, don't worry about it. It's just the warning, not the end of the world. But this warning ended up being a pretty important one. I'm just going to run this real quick, and then we'll talk about that warning. So we get memory address. Here's the whole string. Here's bucket 4, directly accessing it from memory. And then here's bucket 4 using the array syntax for reaching it. Here's bucket 4 2 different ways. I can use a normal syntax for arrays, just like we would in Java or Python. Or I can say, go to the base address, add 4 to it, so take 4 bite-sized steps in memory and give me the value that lives there. That's what that little asterisk there means. Okay, So that's why we got these O both times. This is bucket 4. All right, so now where we ran into trouble last time is when I tried to set bucket 5 to a B, that worked. When I tried to set bucket 6, so S plus 6 equals C, and then I tried to print it out again. Actually, I think just setting it is gave us the error. So there's our segmentation fault. All right, now I'm going to compile this again. Notice the warning we're getting. It's saying ISO C++, so this is a updated version of C++, which is, it's not that guy's fault. I kind of showed you that strings exist in C++ now, but in the early days of C++, I think I mentioned they did not. We used to have this thing called the standard template library, which gave us this type called a C string. But now we use strings kind of like our normal strings that we expect from languages like Java and things like this. But right now, because we're kind of drilling this idea of pointers and memory, I'm avoiding anything new and focusing on this like specialized syntax for pointers, because that's really the thing that's missing from Java. Java, they'll say, a lot of books will say Java doesn't have pointers. The reality is Java does have pointers. It just doesn't have a special syntax for working with memory, where C and C++ give us this asterisk as well as an ampersand for going back and forth between memory and the value at a place in memory. All right, so it's saying, read this as, the newer version of C++ forbids converting a string constant or a string literal to a char pointer. Effectively, it's saying there's a new way of doing strings. Okay? So when I try to set S equal to hello directly, it's saying this isn't something that I allow you to do. It creates it as a constant non-changeable value. That's why the first bunch of things I tried to do did work. It printed out the whole thing of hello. So its statement that it forbids it isn't entirely true, but it's treating it as protected memory. So when I go and I try to write directly, right here, if I try to write directly to memory, it's dying on us. I think similarly, it'll die on us here. Yep. So I can initially fill the array, the char pointer, with a string literal, but at that point in time, it's locked in. I can't go and make changes to it. Okay, that's where that segmentation fault comes in. So if we're focusing on using older style C to kind of drill these pointers, which we use pointers all over the place in C++. It's not like I'm showing you this old school way of doing things and we're never going to do this again. I just happen to be trying to use the example with strings because we're pretty comfortable with the idea of a string in general. All right. So in order to pull this off, as you notice, I have it commented out here, we actually have to use an old C function that lives inside of string.h. And this function is called string copy. So it's a special kind of function. String copy takes in 2 parameters. The destination, where do you want me to copy this to? And the string literal that you want us to copy there. And it does the magic of loading the things into memory the correct way. All right, that makes some sense? So I won't change any of the rest of the code. We just saw it gave us a segmentation error a second ago, and now it won't, because now and it also won't give us that warning. Now we are appropriately using old style string literals with char pointers. But now this is where things, so now we'll pick up where we left off last time. So any questions about that?
I have a question.
And this isn't necessarily something you'll have to do that often in this class, but right now I do want our mindset to be in this idea of memory, 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 memory. All right. How do we access it directly? How do we walk through it? Because we're going to be dealing with pointers on basically every single assignment in this class. All right. And you'll see we can also set bucket 6 equal to something. Go ahead and compile that. No error there. So notice the syntax difference. This is kind of Java style. Set a bucket of an array equal to something. And this is cool kid style, where we're saying, go to a place in memory, add 6 to it, and set the value that lives there equal to this guy. All right, this would be called pointer arithmetic. Okay. Now, keep in mind, or look up here. Well, first of all, I'll just go ahead and prove it right now. I'm going to change that 7 to a 3. What does this imply? If I change that 7 to a 3 right there, I'm doing what now? That line I have highlighted, what does that accomplish? Okay, so I'm creating enough memory. I'm asking the operating system for enough memory to hold 3 chars, right? So what are the legal buckets of a 3-char array? 0 to 2, right? It's got 3. If the length of the string is 3, the legal buckets are 0, 1, and 2. So what do we expect to happen right off the bat? Is that string longer than 3 characters? Yeah. So we would expect there to be a problem right off the bat. Notice there's not. What does that mean? That means that now in Java, we'll get things like an array index out of bounds, right? So if I try to access bucket 4 of a 3-element array, the last element I'm allowed to access in Java would be bucket 2. So if I try to access bucket 4, I'm going to get an error saying array index out of bounds. You walked off the end of that string, right? I promise you, we're walking off the end of the string right here. See, he's cool with it. Who knows what else we're damaging, right? This is like buying some land, building your house, and then building a boathouse in your neighbor's backyard. Without asking, you just go do it, right? No consequences. So even though we're being, nice here to the operating system to say, look, give me some memory to hold my string. Give me three buckets to hold my string. And I'm going to ignore, because I didn't want to pay as much for the land, right? So I'm going to go ahead and I'm going to put a 5-element string in the memory that you gave me. So this is like you're building a house that's kind of hanging over to your neighbor's yard, that type of thing. So I'm walking into areas of memory that I don't own. Operating system gave me 3 buckets. I'm already dealing with 5 in terms of what I initially loaded into memory, right? But then I'm making it even worse where I'm putting stuff later on. So I can come in here, I can say, hey, let's go to bucket 7. So I use string copy initially to put hello into there, so in bucket 0 to 4, right? Even though it only has 0 to 2 as legal buckets that I asked for. That's the land that I own. So I broke the rules right here. We built our original string using too much memory, using more memory than we asked for. We saw that it worked because we printed it out. Now I'm going to go ahead and I'm going to put at bucket 5, which also doesn't exist. I'm putting a little addition in my neighbor's backyard, right? So I'll put in bucket 5 a B, and then I'm putting in bucket 6 a C. I'll put in bucket 7 a W. I'll go ahead and I have this little for loop here. We'll put in before the for loop, I want to do this. We're going to just set bucket 13 to Z. Now I only asked for 3 buckets. So anything larger than a 2, and we're we're building houses and stuff down the street now, right? And we are not on land that we own anymore. So I'm setting bucket 13 of my character array equal to a Z. When I only have 3 bytes, bucket 2 is my last one. And then I'll go ahead and print out that string. So notice here we have our hello BCW, but we don't see that Z. I put that Z in there, right? You saw the line of code. Right here, bucket 13, I put a Z. But the last thing we actually see is a W. So I see the W right here. I would have expected to see the Z kind of out here somewhere. So what does that imply about the default value of memory? I mentioned last time that we have a string termination character. What's the string termination character? It's the character that C uses or C++ uses to know we're at the end of a string. \0. So it's single quote, \0, single quote. That is a single character with the backslash is an escape character. All right. So this is telling me, since I know I put a Z over here somewhere, right? Since it stopped my string right after the W, it's telling me that, oh, that next bucket must already have a \0 in it. That must be the default value of a bucket of memory if nothing else was loaded there. Make sense? And we can prove this by going into our code here, and I'll go from bucket 8 to bucket 12 and just put spaces in there. I'll overwrite the \0 default value with spaces. Okay, that's all I did. I just did everything between bucket 7 and bucket 13 and filled it with spaces instead of whatever the default values were. And now when I print out my string, notice I get my Z. Because this bucket right here was no longer a \0. This was no longer a \0. This was no longer a \0, so on and so forth. Now the first \0 it hits is at bucket 14. If I set bucket 14 to something other than a \0, like a 9, now bucket 15 will be the first \0 it runs into. But now we can hijack this a little bit. Now that we know that when we go to print out a string, it's looking for that \0 for where the end of the string is. We know that we have, we own this memory. That's what we own. We are building down the street over here. That's memory we don't own, but C's letting us do whatever we want, which is dangerous, right? From the operating system's perspective, it's willing to hand that memory out to another program. Make sense? I'm building in land that I don't own. Okay. So I can short circuit this. And I can say something like *s plus, let's do 9, is equal to a \0. So I'll just go ahead and artificially insert a \0 somewhere right in this zone right here, which means that I will have changed where the string termination character is. That will keep me from getting to the rest of that string when I print it. All right, so see, we had the full string here. Then we wrote a \0 somewhere right in this zone right there. And then when I printed it out again, it gave me the end Here, let me see if I can. That's where it ends right there. So this is bucket 7, bucket 8, bucket 9 was my string termination. So this is hello BCW space. Make sense? So at this point, we are directly manipulating memory. That's what we want to get out of this. All right, questions about any of that stuff? Did I show you the ampersand? Let me just do one more thing here at the end. Did I show you the syntax? I showed you, well, we've looked at the star syntax quite a bit for getting the value that lives in a memory address. Did we look at an ampersand? Okay, let's look at that now real quick here at the end. So I'm going to go ahead and just create a couple of integers. I'm going to say int a is equal to 5. I'll say int pointer b, actually let's call this guy a pointer, is equal to the address of a. So variables, the way we define variables is by the type, variable name equals the value, right? The type of this first variable is type int. The type of the second variable is type int pointer. That is, a pointer is a variable that is capable of holding the memory address of an integer. Not an integer itself, the memory address of an integer. This first guy knows how to hold an int. This guy knows how to hold an address. Make sense? Because I've changed the type in front of it. And notice here, what I loaded into it, see if I just put an a in there, a is an int. So that's the value 5. I can't put an int literal into something that's expecting a memory address. So if I want to get the address of a, you put the ampersand before it. This says, give me where a actually lives in memory. Where could I travel to and actually find that 5? That make sense? Now I could say int b is equal to the value that is found at a pointer. And then I can say int pointer, b pointer is equal to the address of b. And then we'll print some of these things out. We'll say cout a and L. So that'll print out the value of a, which is a 5. We'll print out a pointer, which will print out the value of a pointer, which should be some memory address, wherever the operating system decided to allow us to store that 5 in memory. Then we'll print out b. The value of b will be equal to whatever value was found when I travel to a pointer. I will copy that value into b. So b presumably is at a different memory address than a, but now I've copied the 5 that was found at the location of a into b. Lastly, we'll print out b pointer. And b pointer is the address of my variable b. Okay, so a is a variable, b is a variable. These are 2 distinct variables from each other, right? Which means they live in different places in memory. So when I print out a pointer and I print out b pointer, these should give me 2 separate memory addresses because I'm remembering 2 different things, even though they happen to be the same value. I'm remembering the number 5 over here, and I'm remembering the number 5 over here. 2 separate places I'm remembering a 5. Okay? So we'll see a 5, a memory address, a 5, a different memory address. Five, memory address, 5, different memory address. And notice if you do the math, that different memory address is 4 bytes further down because the size of an int is 4 bytes. It just so happens that the operating system handed us a memory address and then also gave us the memory address right next to that guy because it kind of allocated some memory space for us for this program. So the place where it's feeding from when it's handing us memory addresses is all in the same little zone. They don't have to be in contiguous memory for these, but it just so happens that they are right next to each other. All right, so that introduces this syntax for these ampersands. So ampersand takes a variable and gives you the address where it lives. So it's how you get the value of the location of something, not the something that's at the location. If you want the something that's at the location, you use the asterisk syntax. So let's get that into our pointers in C/C++. We have, I'll actually put the thing in there is many books say that Java does not have pointers. But the reality is that Java decides whether something is passed by address or passed by value for us. Therefore, it does not provide us with a special syntax for dealing with memory, i.e. pointers. It's not that it doesn't exist. It just doesn't give us a syntax for working with it. Okay? I probably have an Eclipse open here. I can just show that to you real quick. So I'll just create like a random object real quick in, well, actually, we'll just create an array. Probably we've even done this in here. Yeah, I've done it in here already for a different class. So here is an integer array I defined, right? And then right here, I'm printing out the value of AR. The value of AR, even though we built an integer array there, and then we filled it up with a bunch of integers, the value of AR is a memory address. That is the base address where that integer array lives in contiguous memory. So if I go to run this, there's memory address. We don't have to work that hard in Java to start seeing pointers. Right? So when books say that pointers don't exist in Java, it's a flat out lie. Right there. Half of my output is pointers. Okay? In this little example program. We just don't have that asterisk or that ampersand syntax for directly working with memory. Java denies us that flexibility. Now, we can make the argument that, well, why does Java take that power away from the programmer? You know, kind of we feel like we have one hand tied behind our back type thing. The other hand, Java would say that, you know what, I'm doing you a favor. I'm helping you be a better programmer so you don't have to think about things like that, right? You don't have to think about what should be, when do you pass an address to a function versus when do you pass a copy of something, pass by value versus pass by address. Java kind of makes the best decision for us most of the time. Now, Java attempts to be as efficient as possible, but the idea here is that integers, for example, are always passed by value in Java. Go ahead. Question, my volume is low on Zoom? Well, I didn't change any setting.
Can you hear me?
Let's see. Yeah, segmentation errors on the program. Oh, I see. It says my volume is low, you think. I
Can
didn't
you hear?
change anything with my microphone settings. Is it usually low for you? Oh. Well, somebody say something.
Hello, can you hear me?
Yeah, I can hear you just fine.
Could you before?
Well, I presume no if you tried to speak. My guess is you were muted.
Okay, never mind.
But I mean, I'm not sure, but yeah. I don't think I didn't change anything, and I'm pretty sure, I mean, my volume was on and everything. All right, but regardless, we're in good shape now. What was I saying? Java takes away that decision making for us. And then I mentioned something along the lines, and let's put this in a slide just so we can kind of see the math, the difference here. So, where is this? In Java, primitive types like ints are always passed by value. Okay? And object types like classes and arrays are always passed by address. All right, that's a truth in Java. So here's a follow-up question to this. Is an array always smaller than an int? Can you give me an example of an array that is actually smaller than a single int? That implies the answer must be an array potentially could be smaller than one integer, right? For instance, a char array that has one bucket in it. That would be smaller than an int, right? Size of a char in Java is 16 bits because it supports Unicode, and 16 bits for a single character. 16 bits is smaller than 32 bits. So if I say something like char array AR is equal to new char array 1 is technically less than int A is equal to 5. Right? It's a smaller value. This is 16 bits versus 32 bits. Yet what I'm saying is in Java, these 16 bits are passed by address, and the 32 bits are passed by value. So that comment that Java makes these decisions for you and attempts to make smart decisions isn't, well, the attempts part is, I guess, true, but Java doesn't always make the perfect decision. Right? In real life, remember, we're using programming languages to solve problems similar to the problems we have in real life. Okay, so in real life, if you're having a party at your house, and you probably heard this example from me before, but let's connect it back to this. You're having a party at your house, and you're inviting your best buddy Mike to your party. Do you give me the address where I can find your house, or do you hand me your house? Which would you do in real life? You give me the address. Why wouldn't you hand me the house? Well, I could. If I had the house, I could just open the door. I'm there. Saved me a lot of commute time. Why don't you hand me the house? Don't overthink it.
If I don't want to give you the house,
It's heavy. Even if you wanted to, you couldn't. I mean, you look fit enough, but I don't think you can lift a house, right? Okay, they're heavy. Houses are heavy. So in real life, we would never hand somebody a house because it's too heavy. It's easier to hand them a little piece of paper or send them the modern thing would be send them a text with the address of where I could find the house, right? But if we use a real life example, is there an example where there is a house in real life that actually would be smaller than that piece of paper that has the address of the house on it? Maybe not a human house, but something for like an insect or something like that. We could say maybe, right? So somebody throws one of those little, just the starter hornet's nests, just toss it at you. the ones you find in your barbecue grill when they're just getting going, those guys. But generally speaking, in real life, we would always give somebody the address of a house because houses are heavy, right? So that makes sense. In Java, the idea is that objects and arrays are kind of like houses. So Java has just made the decision that we will always give you the address of an array or the address of any instance of an object because these things are likely heavy. Make sense? Even though I said in real life, you probably could find some little insect house or their burrow or whatever. You could find something that is so tiny that it actually probably would be more efficient to hand me the house than to give me the address where that house lives. Okay. But it wouldn't be that big of a deal if you just handed me the address, right? The difference in size isn't huge. So in this example I'm giving you right here, this Java example, technically we would say, you know what? If we're just being super detailed about this, you're actually better off handing me the value of AR rather than the address, technically. Because in the address of AR is actually 32 bits in most operating systems, or a modern operating system might be 64 bits. That's how big an address is. Well, 64 bits is a lot bigger than 16, 4 times the size. But it's still not a lot of, it's still fairly light. It's like the difference between handing me a Post-it note and maybe like a letter. Okay, something like it. Both of them a human can hold. Okay, it's not the end of the world. But now we go the opposite direction. We use that example of a house, right? It would never make sense for you to hand me a house in real life because they are always going to be heavier than the address of a house, right? All right, so we would say that Java makes the best decision for the programmer most of the time. And even when it doesn't make the most memory efficient decision, it's not off by much. We haven't really cost ourselves that much memory, right? And then at least we can trust that Java is going to be consistent. Because it probably would be more problematic for a programmer if Java sometimes passed a object by value and sometimes passed it by address, depending on the size of it behind the scenes. As programmers, we'd rather just be able to trust that, oh, this is passed by address, even if it happens to be smaller than the value would have been, or larger than the value would have been. Okay. Now let's go. What does C/C++ do? Primitives are passed by value by default, but we have a special syntax in C/C++ that allows us to pass an int or pass a primitive by address. That special syntax is the ampersand. So I can have a function in C that takes in the address of an int. So maybe I have a, void do something with the original, and this guy would take in an int pointer, maybe an int pointer is the name of my variable, something like that. All right, so that maybe is the method header. And then maybe someplace else I have an int a is equal to 5, and then I call do something with the original, and I pass it the address of a. Does that make sense? This function expects an integer pointer. I have an int, but if I want to give it the address where that int lives, I would pass it ampersand a. Here is the address of that integer, as opposed to a copy of that integer. So C and C++ empowers the programmer to make that decision, which then means that in C and C++, it would be possible, if we put this back into real life, it would be possible for a human being, you invite me to your party, it would be possible for you to hand me the actual house if it was that important to you. Lift with your knees, right? Isn't that what they say? Not your back, lift with your knees. Okay? Something like that. So C and C++ gives us the flexibility to do something like that. Which is better? Which is better and why? What do you think? Do you like Java's approach or do you like C and C++'s approach? Okay. What's the downside of that flexibility? Okay. But doesn't it also imply that we can kind of do whatever we want in memory? Didn't we purposely do that here? I asked the operating system for a container that holds 3 things, and then I just went ahead and just did whatever I wanted. We put 15, 16, 17 things, whatever we put in there, more than 3, right? We put more than 3 things in here. So because C and C++ gives us free reign of memory, it then loses the opportunity to control us. So as a C and C++ programmer, we have the power to walk through memory wherever we want, because they've given us a syntax for working with memory. By empowering us to make the choice of whether we pass something by address or pass something by value, that syntax gives us then the flexibility to traipse through memory at our whim, which then allows hackers to do things and virus writers, stuff like that. Go ahead. Well, let's say we'll use a real life example. So I mean, the short answer is yes, it would cause you to, I don't know if overload's the right, it would cause you to overwrite memory that somebody else might be using. If your neighbor just built a swimming pool in their backyard and you come in and you cement it in and put a basketball court, your neighbor's not going to be happy with you. Because you're going to say, look, your property line ended there. I say, yeah, but that's okay. I'm using C and C++, so I wanted my basketball court to be over there, even though it's your land. I just did it. Done. C and C++ will let you do that. Java would not. Okay, so your argument would be that you well, it's not an incorrect statement, but you would say that C and C++ gives you that flexibility, but with great power comes great responsibility, right? Okay, now what's the argument for Java being better? Certainly more convenient, takes that decision making away from us. And I would maybe argue that if you already understand this memory stuff, that Java would, Java feels like it's doing something for you that you like, right? Because you're like, oh, you know what? I didn't like all that syntax with the asterisks and the ampersands and manipulating memory directly. It kind of made me feel cool for a few minutes, and then all of a sudden it's like, this is tedious. Where Java just started doing it for you. We all have probably examples in life where we have automation and things like that. Like I don't even take my car keys out of my pocket anymore because as long as I'm in proximity of my car, I hit a little button, it turns on. I no longer have to aim the key in the dark and get it in there, that kind of thing. So, is that a humongous deal? No, but it's a nice thing to do. It's a nice little, convenience. And at some point in the future, or maybe not even far from, in the future, people who are learning to drive today, because, it's probably 50% of cars have just the button now, something like that. There's going to be some point in the future, people are like, you actually used to have to put a key in there? That was the thing? I mean, because any of us today, we don't know how you used to start the cars back in the early days where you had to get out and crank the engine, kind of like turning on a lawnmower where you're pulling the ripcord. You just have to crank the engine to turn it on, right? Middle of the winter, you're in a blizzard. You can't, I start my car from an app. So it's nice and toasty by the time I get in there. So like I'm going to be leaving after class today. I'll start my car and it'll already be warmed up from here. Where you used to have to go and manually crank the car, but none of us had to do that, right? So we don't necessarily appreciate that, oh, well, I can just get in and turn the key. Now it's like inconvenient to get a mess with the key. So I would say that Java is better as long as you understand what it's doing for you so you could appreciate the work that it's doing. And it's not just providing this kind of magical solution to something that you don't even know it's doing. Java hides a lot of stuff from you. So now an interesting truth. So our history of our programming languages, we went C, then C++, then Java, then C#, right? So what happened historically? C had pointer syntax as well as something called a struct. All right, and we'll work with structs a little bit as well. So C had pointer syntax as well as a struct. Structs are kind of like dictionaries in Python. Name value pairs, that's what a struct is. I say kind of because the default, and this is where it's related, by default, structs are passed by value. Okay? C++ had pointer syntax as well as structs, as well as classes. That's our transition from object-oriented, from procedural to object-oriented. Java removed pointer syntax as well as structs. I'll just put it in parentheses here. Isn't a struct and a class that has no methods technically the identical thing? If we just write a class and we only put fields in there and don't write any methods, potentially, or is that the same thing as a dictionary from Python? Same thing as a struct? It is the same thing as a dictionary from Python, but it's not the same thing as a struct because of the default way it's passed. In Java, classes are passed by address. That's the decision they made, because it says more times than not, a class is going to be heavy. It's like the house, and we're going to pass it by address because houses are heavy. So Java says, if you happen to write a class and you choose not to put any methods in it, and you just have a bunch of fields, making it behave like a Python dictionary or making it behave like a C or C++ struct, it'll behave very, very, very similarly in that it stores name value pairs, but the default way in which it's passed is different. So that pseudo struct in Java will be passed by address because it's technically a class. Yet a struct in C and C++ is passed by value sent by default, because that's just how structs are passed. But in C and C++, we have the power through the special pointer syntax to choose to pass a struct by reference. But the default is by value. Java, we don't get the choice. Java made the choice for us. So technically, a struct and a class with no methods, while very, very, very similar, are not identical. So Java making this decision to remove them, while not the end of the world, was confusing to the programmers who were coming from C++ at that period of time, right? The people who probably moved to Java in the early days of Java were previously C++ programmers. And they're saying, well, what happened to my structs? And the Java documentation would just say, you don't need structs. Just write a class and don't put methods in there. Okay. But then if you're already used to structs getting passed by value and you're making changes to them and you're wondering why other parts of your program are breaking, it's because in Java, those classes are passed by address. So that means when you make changes, there is side effect. Okay. So it's things like that that bother me about Java when you're learning that as one of your early languages. Think about the complexities we're going through here. A lot of this stuff we're talking about in here so far is going to feel pretty overwhelming until you start doing it, right? You know, we're throwing asterisks in front of things and ampersands in front of things. We're seeing scary memory addresses. We're asking the operator, instead of even the keyword new, we're saying malloc, which just feels scarier, even though it's the same thing, right? We're directly talking to the operating system, saying, I need some memory. And the operating system says, here, you got your memory, but then you can just go do whatever you want with it, right? You can walk off the end of it, nothing's going to scream at you. And then all of a sudden you're in this situation where it's not screaming at you, and you're, even an advanced programmer, but certainly as a beginner, intermediate programmer, if it's not screaming at you, it must be okay, right? But it might not be. It might not be okay. In some circumstances, especially if you're dealing with an older operating system, the operating system might not live in protected memory. So you walk far enough off the end of your array, you might start getting into operating system space. All of a sudden your computer crashes and you got to reboot it to reload the OS into memory because you just overwrote part of it. Make sense? These are things that used to happen before our operating systems evolved and stuff like that. And again, that's something that we can't necessarily appreciate today because for us, the operating systems have always done that, right? But in the early days, they were a little bit, that wasn't a problem they thought they needed to solve. Okay, so Java removed that pointer syntax as well as structs. So we're just going to say, no structs are passed by value, classes are passed by reference. C# brought structs back and also brought pointer syntax back. Now, that idea of having direct control of memory, just to close the loop here, having direct control of memory, while nice, can be dangerous, as we've kind of implied, right? So C# forces you to do pointer stuff inside of an unsafe code block. So they've introduced a new keyword called unsafe, where they're basically saying, look, you're the programmer. If you know what you're doing, you're manipulating memory here. If you know what you're doing, let me know that you know what you're doing, or at the very least, let me know that you're taking responsibility for this by putting the unsafe keyword there, curly braces, and then you do your pointer stuff inside of there, because now you've said, look, I got this. I got this. I know how pointers work, or at the very least, if something bad happens, that's on me. Because you only let me do it if I put it inside of an unsafe code block. As long as you look at the unsafe code block and you say, this might be unsafe. Maybe I don't want to do this, or I have a good reason for doing this. Make sense? So we might say that C# is kind of the both and. You get the special syntax if you want it, but it forces you to investigate the consequences of doing that, or at the very least, use some syntax that you found on Google that you don't know what it does, but unsafe hopefully raises some red flag, something like that. Okay, so that kind of covers the gambit, and we went from no pointer syntax back to pointer syntax. So we can say as a modern developer, which is better? I think we could probably say it depends. Okay, right, it depends. So we're going to keep going a little bit here, but I'm going to put up our homework for Tuesday. Write a 2-page paper discussing the differences between C, C++, Java, and C# from the perspective of structs and pointers. So I just gave you the highlight reel of that, right? So investigate that a little bit so that you now gain a deeper appreciation for the languages that you might be working with in industry. Because keep in mind that just because C is from 1970 doesn't mean that you can't get a job doing C development today. Most of our embedded systems, like if you're writing, we were talking about cars earlier, if you're writing stuff for computers and cars, you're probably writing it in C, right? Because those embedded systems, those little tiny computers, because the concept of what is a computer is very fluid today, right? You know, if we went back 20 years, we say, well, a computer is your desktop thing with a giant monitor and stuff. But realistically, is this a computer? Yeah, that's a computer. Is the thing that's running your dishwasher, is that a computer? Absolutely. It might be a little bit less general purpose. You know, kind of only knows how to do a couple of things, but still a computer. Our toasters are now computers. Cars are, I mean, you talk to an old school mechanic, you know, who's been building cars their whole life and stuff like that. You know, they can fix older cars, right? You get this newer car that you open the thing up and it's like interfacing with a spaceship. Unless you have the specialized equipment, the computer systems to plug in and get all the diagnostic stuff and things like that, no longer is it just going in and tightening something up with a wrench. You might have to get a lot deeper into it, and you might not have that expertise because you don't have the equipment to do it or even the know-how to do it. I don't think it's probably that common where a mechanic has to go in and write some code, but it's certainly like my car has, I drive a Ford Explorer. It has Ford Sync software in it. I think it's Sync 3. Maybe every 2 months or so, there's a software update for my car. And if I don't update it, then my audiobooks start getting sketch. Because I think what happens is whenever there's a software update for my phone, maybe the Bluetoothy stuff behaves a little differently or something like that. They might make a change, which technically then makes it incompatible with the Sync operating system. So then the Sync operating system has to update itself in order to make sure my books don't start and stop at bad times, things like that. So my car gets software updates just like my cell phone. Go ahead.
So, just out of curiosity, like I know, so there's computers in your car. Are programmers employed to like deal with the software that's on them?
Both, it's called Android Auto and Apple CarPlay. You can write software. You can write apps in Java for your car. You can write apps in Swift for your car. Yep. Yeah, absolutely. You can be a software developer. I mean, I don't think it's really taken off yet. Same thing's true for smart TVs. You can write apps for LG and Samsung smart TVs. You can write apps for Apple TV. You can write apps for Android TV, which really isn't as popular. Absolutely, yeah. That's where all the apps come from. You know, I get my Slack notifications on here, my text messages. You know, so those, somebody wrote that interface, right? So this mobile app for Slack on my phone talks to the like the widget accessory that's installed on my watch. Those two apps talk to each other so that I can get those notifications over here. Everything is a computer, right? Well, I mean, I would say very useful, but you'll actually do all of them in our program. So, you know, so maybe the broader question is, for those of you online, she asked, how useful would it be to learn some of these legacy languages? Well, it's probably not overly useful to go learn some language, like there was a language called Forth, which allowed you to do like BIOS programming on Mac and stuff. Not that you can't find the existence of a job like that, but it's going to be pretty rare. But you know, you got your kind of your core group of languages where, I mean, C, as old as it is, I mean, we can say it's a legacy language, and it's probably not even fair. I mean, you can find lots and lots of jobs as a C developer. You can still find lots of jobs as C++ developers. You can find jobs as assembly developers. Maybe the main legacy language that we don't teach here that I think would be worth learning is Cobol. And that has more to do with money. On both sides. First of all, you can make a lot of money as a Cobol developer. So Cobol is a language that was built specifically for writing business applications. And the people who used Cobol were a lot of times banks and insurance companies that work with a lot of money. And they've invested millions and millions and millions of dollars into these software systems that now need to be updated for, you know, new changes to things and stuff like that. Now, most businesses, they have a budget each year, right? Now, let's use an example like Northwestern Mutual. We have some former students. One of the students is Nick Largent. He works in Northwestern Mutual, and he does some Cobol development and systems programming stuff there. Well, they have all of this old software, and they might say, look, it might make logical sense to convert this over to Java, maybe something, you know, newer language, but maybe that costs $30 million to do that for as much stuff as they have. I'm just making up a number, and frankly, I think there's a better chance that my number is low than that my number is high. So let's just use the $30 million number to convert it all, $30 million plus time, right? To convert it all over to a newer language. But maybe their budget for their software operations is $10 million a year. And they can pay developers who know Cobol to keep maintaining it and updating the Cobol code and keep within their $10 million a year budget. Because it would cost triple their budget to update it to something newer. And even though you would say, well, they break even after 3 years, they might say, I don't care. My budget is $10 million. Does that make sense? Because they have to do operations based on what their revenue is. So if they don't make $30 million, which they do, they make $30 million, a company like that. But you know, if they didn't make $30 million, they couldn't afford to pay $30 million. So 10 million is just part of their budget numbers. All right, makes some sense. So I would say if you were going to pick those languages that are worth learning, I would throw Cobol out there as like this outlier. But Cobol's also kind of funky. in big cities, so or even medium big cities like Milwaukee is bigger city-ish, not as big as Chicago, but in those kind of cities, there are jobs dealing with COBOL that pay a premium. And the reason is that schools are no longer teaching COBOL. It's just not a common thing. But again, I teach programming from the perspective that computer programming is the skill set. The language doesn't really matter. So you can go and learn, how do I declare variables in COBOL? How do I go and write loops, ask questions, repetition, those kind of things, and learn COBOL relatively quickly. COBOL typically runs on a mainframe, so you actually have to get an emulator in order to practice writing COBOL yourself. Now, my wife is a COBOL programmer. She's been writing COBOL since, well, we had it in school. So she's been a COBOL developer since 2000, but she works at Western Illinois University where I used to teach, which is in the middle of nowhere. So there, and right now they're going through a hiring process looking for some COBOL developers. They're starting to move towards switching over to a new system that uses Java, but that's a pretty far off way for them right now. But they have a very limited talent pool to pull from. You know, there's not a huge, I mean, this is out in the sticks in Illinois. So not only is it downstate Illinois, i.e. not Chicago, it's like out in the country, like Macomb, the city where the university is, that's the big city. And Macomb, I think, has a population of like 8, if you subtract the university from it. It's a tiny town. You know, they have a Walmart. That's it. They have a Walmart and one grocery store and a university. That's what the town has. You know, so all of the towns around there that feed this from an employee perspective, they're super tiny towns, right? Like unincorporated and stuff like that. So they have a very small talent pool to pull from. But because of the historical nature of this job there, they also don't pay very much, because the job working at the university for COBOL, that's why I didn't use universities as an example. A lot of modern universities use like Banner. We use a pre-created package for doing these things. Where at Western, they've been writing it for years and it would be too expensive to change it. They have all this custom stuff. But it's under a union. So they're civil service employees. And I think as a beginning COBOL programmer, an entry level, the pay is like $35,000 a year. Now, that's $35,000 a year in Midwest sticks money. So maybe that's closer to like 50,000 a year or 45,000 a year in like Milwaukee dollars, but it's still not that high paying for a computer programmer when you can go work at Northwestern Mutual right out of school as a COBOL programmer and probably make 75. Make sense? Just because it's a legacy language that they still need people to do it. And all of the COBOL programs they have are either retiring or dying because they're old, right? So it's a real problem. So if you wanted to find that niche language, I would learn COBOL, but otherwise C, C++, Java, C#, Python, the web languages like Node.js, things like that, SQL, which isn't a programming language, but it's talking to databases. And then if you want to dabble in Apple stuff, Swift. I would say anything outside that list, you're probably wasting your time in terms of what you'll get your job in. A couple of languages have some, like Google's Go language seems to be gaining some popularity, but I don't really know what niche it fills. So that's one of those things, like you maybe use it at a hackathon or something like that and say, I'm gonna play with Google Go. But other than that, I wouldn't go far outside of those languages other than just challenging yourself for a weekend or something. I don't remember if were you in my class when I was on that cruise and I decided to learn the chicken language?
Yeah, I told you to learn that.
Oh, that's right. It was your idea. Yeah. So but I had to write an interpreter for the chicken language because it was each instruction was some number of chickens. So what I did is I wrote a Python interpreter that allowed me to say, well, I really want to say this, and it just generated the correct number of chickens for that. So my output for this program was like 7,000 chickens, and I wrote a dice roller in chicken language. All right. So there's your homework for Tuesday. Hopefully our virtual machine is all good to go on Tuesday, and I'll do a fairly quick tutorial because my plan is to have it already installed, and all you have to do is say clone Littman's Unix machine, and I have a fully up and running Linux whatever 2 minutes later, that kind of thing. And then we're going to start dealing with objects in C++, kind of writing something like we wrote last semester. We'll probably start off with like a dice roller type thing just to see how classes and header files work. All right, do spend some time reviewing the stuff we talked about today. I know it feels tedious, but it's super, super, super important. And if you don't wrap your mind around pointers, you're going to get lost pretty quickly in C++. All right. I will see everybody on Tuesday. Make sure you keep an eye out for my Hearthstone live streams. What is it? Like, subscribe, punch that little bell. I'll probably do one tonight. I was supposed to have golf league tonight, but I think my wife's going to make me stay home with the weather, which is okay. My partner for it, we play in the golf simulator at the club. My partner lives in Tosa. So, and he's a younger guy, wife's pregnant, and I don't think you need to have a 45-minute drive in snow when you could just play golf league next week. All right.
My question, my